Sorry. Okay. Okay, so for the tutorial one, actually you need to model adjustable of DC motor to control the speed of DC motor for fan application. This one, air blower application. Sorry. So actually, it will create a load profile. So where the load profile is PL. PL is the load top. Load top. So depend on the application where it will create the air resistance. The air resistance will be larger when the motor rotates faster. So that's why we can model the load top as 0.0955 multiplied by speed. Okay. So remember the speed you must obtain the value must be in SI unit in radian per second. So this case the desired speed is 1200 RPM. So mean you need to transform the unit from RPM to radian per second. So remember how to transform the speed. So the desired speed is 1200 RPM. So you have to convert it by multiplying what value? 5 divided by 60, right? 2 pi divided by 60. Is it true? Sorry, 60 divided by 2 pi. Sorry. RPM, so you have to multiply by 2 pi divided by 60. So then you get in radian per second. Okay? Remember. So this is the conversion from RPM to radian per second. RPM is rotation per minute. Is it right? Rotation per minute. Okay, so actually you need to compare the efficiency performance using two methods. So the first method using the rheostat and the second method using the power electronic converter. So in order to have fair comparison, so you must apply same DC input voltage. So this case VDC is 200 volt. So same goes here, 200 volt. And because we want for fair comparison, because we need to compare the efficiency performance from these two methods. So the desired speed also must be same. 1200 RPM. This one also 1200 RPM. So it means in order to get the same speed value, so both technique must produce same torque, right? Same torque, same current, same voltage applied to the motor. Okay, so how to calculate, how to obtain the value of speed, the value of voltage, current, and torque in order to get the same desired speed in 1200 RPM. Okay, so this is the solution. Okay. So first, in part, you need to construct the model of the motor. So this one we have discussed in class. Sorry. Okay, so you have you need to apply suitable symbolic block in order to construct the model. So actually, this model can be constructed using the equation that we have discussed in class. Clear? Okay, good. Maybe I need to turn to the page. How to model the motor? This one. So you have to apply this equation. So remember, initially you start from the motor equation, DC motor equation. So then you need to transform S domain. You must get all equation in Laplace transformation. From this equation, then you get this equation, 13 to 15. So then you can apply this equation to construct the model. So this one I have discussed in class. No need to discuss here. So then for tutorial, so actually from the model here, you need to put extra block. Okay, maybe I need to use different color here so that you can differentiate. So this speed, you need to multiply by 60 divided by 2 pi. Okay. So this is the pi. Because the speed used to construct the model is SI unit. So you need to convert it to RPM. So then we can check. That's it. Your selection of your start resistance value and duty ratio will obtain the desired speed 1200 RPM. So that's why you need to do the transformation here, from radian per second to RPM. Then the motor you connect directly to the DC voltage. So where this voltage is the VA. What is the required VA so that the motor can rotate 1200 RPM? Okay. In order to calculate the VA value, so this is the answer. Okay, so you must start in order to calculate the desired armature voltage, which is VA. So you have to calculate the torque first. So where the torque is PL, right? Okay. So based on the information given in the question, where your TL given is 0.0955, you multiply by speed, the desired speed. So since we consider analysis for the steady state, so mean there is no change of the speed. So this term you can neglect because no speed change, because the speed we assume is constant, right? And speed steady state. Okay, B is 0. So you can refer to the question. B, this case, the friction. Viscous friction is 0. Okay. So we can simplify our analysis. So B is 0. No speed change because speed we consider is steady state, constant. So the only term that left is load torque, TL. So then you can straightly calculate the TE. 955 multiplied by speed is 1200 RPM. So remember, in order to apply the equation, so you must convert all parameters in SI unit. Okay? So you multiply by what? 2 pi by 60. Then you can solve. The torque required is 12 Newton meter. Clear? So we know that the torque, you can express the torque equation in terms of electrical parameter. So the previous one here is the mechanical because it involves J, moment of inertia, and friction, right? So you can rewrite the torque equation for another form based on the electrical parameter, which is KT and IA, right? KT is the torque constant. Okay. So then you apply this equation to calculate the required armature current, IA. So from here you rearrange, then you can solve for IA divided by KT. So your torque is 12 as calculated above, and KT is what? Refer to the table in the question. What is the value of KT? 0.0 0.5. Okay, yeah. KT and KE are same. 0.5. Then you get the value is 24 ampere. Okay, then finally you can calculate for VA and the desired armature voltage to be applied across to the motor input terminal. So VA is IARE so this KE. Okay, so this the second term you can neglect because we focus on analysis is on steady state where the current is constant because we need to get the speed also constant. Then you can reduce the equation. Then you can calculate the value of the VA. IA is 24 multiplied by RA. RA's value is what? What is the value of RA? 1.2. 1.2 plus 0.5 multiplied by speed. Then you get the required VA or the desired VA is 91.63 volt. Okay. Actually, in first part, you do the construction and model of the motor in order to verify your model is okay or not, is right or not. Then you can supply the voltage, which is 91.63 volt. Then you run the simulation. Then you check, is it your speed? Obtain the desired speed, 1,200 RPM. Clear? Betul. Okay, for the first part, part 1. Okay, part number 2, we move to the part number 2. So this, in part 2, you need to compare the efficiency performance by using these two methods, using rheostat and PEC. Okay, so in order to obtain the same speed, 1,200 RPM, so in this case, the VDC is 200 volt. Here, 200 volt. Method 2 also 200 volt. So your targeted speed is 1,200 RPM. So here also 1,200 RPM. So what is the value of A here? As calculated in part 1, which is 91.63 volt. Okay. So in method 2, VA, so actually you obtain the average value and the DC component. It's not the, because the VA waveform in method 2 is not continuous. Okay? It's discontinuous in square wave shape. So you must calculate the average value. So the average value must be same, which is 91.63 volt. Okay, so we go back to method number 1. In order to step down the voltage from 200 volt to 91.63 volt, so you must calculate appropriate value of rheostat resistance value here, the RH here. So to calculate the RH, so you can apply this equation, the difference between input and output, or the armature voltage, then you divide by IA. This one simple, kan? You just apply apa? Kirchhoff voltage law, voltage divider rules, basic electric circuit theory. Then you can calculate for RH. 291.63 divided by 24. So the resistance value is 4 ohm. Okay. By calculating appropriate value of your start resistance value, so then it will produce the a suitable drop voltage across the. So then you can apply Kirchhoff voltage law. And the input is 200, which is larger than the desired VA. So then they have drop voltage across your start resistance. So that's why you need to calculate appropriate value of RH, your start resistance. Okay, this is simple technique. Okay, then method number 2. So to obtain the desired speed, the same desired speed, 1200. So means your current, your VA must be same as method number 1. So in order to calculate, to step down the voltage, so you have to calculate the desired duty ratio. So where D is, your VA is 91.63, then divide by 200. Okay, so you get the value is 0.45. So make sure your D value must be in range between 0 to 1. It cannot be larger than 1 and it cannot be negative value. This is the duty cycle of your pulse width modulation here. Okay, so mean you need to design your PWM and so here is your T on, right? This is your T on. Then here will be your switching period. Okay, so your D you can define it as here, and also this one. Okay, so you have to design the PWM waveform in order to obtain the desired VA, which is 91.63 volt. Okay, then next page. So this is the expected waveform in method number 1. So you can notice that the voltage across the motor VA is continuous, straight line. Because your current also continuous. All elements are connected in series. Okay. So this is your VA as calculated above, which is 91.63 volt. IA is 24 ampere. So where the IA is the armature current flow to the motor. So all current flow to each element is same, sama. Because all elements are connected in series. I battery and IA are same. So IA and I battery is 24 ampere. So VA and IA waveform are continuous. Okay. So but based on this waveform or n calculated value, so then you can calculate the input and output power. Then after that you can calculate the efficiency performance. So here P in, the input power is, the input is VDC and the battery voltage, then you multiply by I battery. So the VDC is 200 volt, the battery current is 24. 4,800 watt. For P out, VA and IA. And VA, the armature voltage. Your VA is 91.63 volt. Current same, 24. Okay, from this, from here you can calculate the losses, the power dissipated in rheostat. So your P loss. So this is power. Maybe I write dissipated in rheostat. So where you can straightly calculate for P loss, which is IA squared RH. 24 squared. The RH value is what? 4.54. Then you get the losses power is 2,687 watt. Very significant power loss. So you must put heat sink attached with the rheostat. Then your system will be bulky because you have heat sink rheostat. Actually, you can check your calculation here. You can apply another equation where the P loss also the difference between P out, sorry, P in and P out, right? The input power and P out. This one just to double check your calculation. Okay? The input to subtract with the P out. Okay, then you can calculate the efficiency. Where the efficiency is P out divided by P in 100%. Then you get 4.4582%. Very low efficiency. Right. Okay, so this one for the calculation for method number 1. And actually, for part 2, you need to compare the efficiency performance obtained in method 1 and method number 2. So this is the process. First, you need to know how to sketch the waveform, calculate the input, output power, the losses, and efficiency. So we go to the method number 2, using power electronic converter. PEC stands for power electronic converter. So before we sketch the waveform, so maybe we can write the expression of the armature voltage, VA here. The voltage across the motor. Sorry. So where your VA, it can be either positive VDC and 0, right? So VA is VDC when the IGBT is turned on. Simple, and IGBT is turned on, short circuit. So we consider the IGBT is ideal switch. So when the switch is on, then it will create short circuit here. Then you apply Kirchhoff voltage law, then you get VA equal to VDC. Otherwise, when the switch is off, the diode will turn on. The field divider is turned on, right? So when the diode is turned on, then it will create short circuit here across these two terminals. These two terminals. So then that's why your VA will be 0. Okay, because your current circulate into this loop. Okay, VA is VDC if IGBT on. VA is 0 if IGBT off. So how about the battery current? I prime battery. This current. The current flows out from the positive terminal of the battery. So for I battery, so it can be either I battery is same as armature current, right? When the switch is on, if IGBT on, otherwise the battery current is 0 if IGBT off. So based on these two expressions, then you can sketch the waveform. Saya nak sketch the waveform. So your VA is varies between positive VDC and 0, right? When the switch is on, VA is VDC. But when the switch is off, it will be 0. Okay. So from 0 to DT, so this is the time taken for the switch is on. From DT to T, so this is duration for the switch to turn off. Clear? So this waveform will be repeated for the next cycle. So remember, for PEC, the output voltage is in square wave shape. It's not as in method number 1. Your voltage and current is continuous. So by applying appropriate value of D, then actually you can get the same desired voltage VA, 91.63. So that's why you have to design properly the PWM, pulse width modulation signal, to be injected to the IGBT. Okay, this is the VA waveform. So for IA, so remember your motor is the inductive load, because across these two terminals, so you will have the RA, armature resistance, armature inductance, and EMF. Due to the inductive load, your current flow through the motor, it cannot instantaneously change. You know, instantaneously means your current cannot suddenly reduce to 0 or suddenly change the polarity from positive to negative. It must have time for the current to charge and discharge. Okay, so that's why your current is in triangular wave shape. It must be in triangular wave shape. So means maybe I write first. Okay, the armature current. Okay, the green color is the armature current. So when the switch is on, the current will be charged. Right. So this is the case when the current, the switch is on. Current is charged. So mean your current will flow from the battery, flow through the switch, because switch is turned on. Then motor complete to the negative terminal of the battery. Okay. So the green current indicate the current flow when the switch is turned on. So this is the waveform. Okay. But when the switch is off, maybe I use blue color. Okay. So switch is off. So mean the IGBT block the current. So the current in the inductor, because inductor is the energy storage, it release the energy. So it must have a path for the current to flow, to discharge. So the only path that it can flow is through diode. So that is purpose of inserting the diode across the motor because we need to provide alternative path for the current to flow. It cannot flow through the battery because the IGBT is open, right? So then current will flow from anode to cathode to turn on the diode. Diode is in forward bias, then it will circulating through this loop. Okay. So it means here your current will be discharged linearly. Okay. Okay. So the current in triangular wave shape. It's not constant due to the switching effect on off. Okay, so this is the armature current. So for the battery current here. So maybe I use highlighter, yellow color highlighter. So based on this expression, so when the switch is on, IGBT is on, the current same as IA. So mean your current will be charged. Yeah. But when the switch is off, IGBT is off, then current can immediately reduce to 0. This one, okay. Because at the input side, there is no inductor. But at the output side, you have inductor, LA, armature inductance. So your current cannot immediately reduce to 0. So then your current battery will change immediately to 0 during switch is off. Okay. Then when the switch on again, then current jump to here, to this point. Then it will be same as IA. 0. Okay. So the highlighter with yellow color is the battery current. So in this case, you can notice that the battery current, the current is discontinuous. It's different with the obtained in method number 1. Method number 1, the battery current is continuous. Always the power consumed. The power is always consumed in method number 1. But for the method number 2, the power is consumed from the battery when the switch on. But when the switch is off, there's no power delivered to the load. Okay. So maybe we can save the energy and also improve the efficiency performance by using the method number 2. Okay, if you can in this graph also plot the battery current, the orange color. Okay, so means here the orange. So this is your I prime battery, where the current is discontinuous. Discontinuous current. Okay, how to calculate the average of I battery prime? So in order to calculate the average component for the battery current, so you can apply this equation. So you integrate from 0 to T. So here is the I prime battery. T with respect to the time. Actually, you just integrate from 0 to dt, because from dt to t, the current is 0. Right? Yes. On your yellow line, this point. Yeah. From 0, suddenly jump to this point. Because your IA is continuous, triangular, right? Charge this. So you need to refer to this expression. Then you can understand. Okay. So you agree that for the inductor current, for the motor current IA, the current will be in triangular wave shape here. Because we consider the motor now is in steady state. Initially it start from here. Okay. So that will charge, discharge, charge, discharge. Okay. So when you refer to this expression, when the switch is on, so automatically your battery current will be same as IA. Okay. Is it okay? Yes. Okay, so from this equation, actually you can calculate the average by multiplying IA and D. IA and D. D is the duty ratio. So here is 24 multiplied by D. D is what? You calculate above, kan? 91.63 divided by 200. Then you get the value is 10.9956. Okay, so then you can notice the value, the calculated value 10.9 is less than that, but is less than that produced of the battery current in method number 1. Method number 1, the battery current is 24 ampere. Okay, in method number 1, your battery current is 24 ampere because IA and I battery always same. Because all elements are connected in series. There are no switching. Okay? So battery current here is 24 ampere. But for method number 2, the average current is 10.9. Less than that obtained in method number 1. So then you can calculate the input power P in is VDC multiplied by I prime battery 200 10.995, then you get 2199.121, and P out VA multiplied by IA. One 9912. P in and P out same value. Because this is the ideal case, ideal switch. You use that. We consider to use ideal switch for the IGBT. So then you can calculate the efficiency power is P out, P in 100%. Then you get 100% efficiency performance. So this is for ideal switch. So P loss is 0 because P in is same as P out. P loss is 0. Okay, finish. So make sure you understand. For example, if the question given, you need to provide a solution to compare the efficiency performance between using rheostat and powertronic. So in question, maybe it provide the parameter values for RA, LA, J, B. So then based on the parameters values given, then you need to calculate the desired VA and IA and torque. So you have to refer to this procedure. And you calculate the required VA, IA, torque. Then you must able to sketch the waveform. Remember, for method number 1, rheostat, the current and VA is continuous straight line. But for in method number 2, so you need to consider the expression when the switch is on and switch is off. What happened? So then you can sketch the waveform. So after that, you must know how to calculate the input power, the output power, and also the efficiency. So from there, you can compare the efficiency performance obtained in both methods. Okay. Okay, so now we go to the demonstration or verification that what we have calculated here. Then we verify through simulation. Okay. So please open the MATLAB. So this is the simulation file that I provided to you. Okay. So actually, the model is completed. It's already completed. Okay, so you need to substitute or apply the calculation value that we have did just now. Then you apply the values. After that, then you can verify. Is it the motor speed reach? Is it the speed obtained is 1,200 RPM? So that you can check using the display block. Okay, please do. I give 10 minutes. Okay, before that, maybe I need to brief. So actually, this is the motor. Here is the motor. So I click subsystem. So you can double click this block to see inside of the subsystem. So this is the model of the motor. Okay. I try double click the block. Okay, then from here you can see there is the current measurement here. Current measurement actually to provide the information of current here, the IA. IA you multiply by KT to produce the torque. Clear? Then torque you compare with the load torque. Then here will be the transformation of the mechanical system. So where your J is 0.05, is it right? 0.05, 0.0005, sorry. So B is 0. So maybe you can resize to see the transfer function equation here. Try resize the block. To mean this is 1 divided by JS. 1 divided by JS because B is 0. There. Here is KE. You obtain the speed, output of the transfer function speed multiplied by KE. Then this will provide signal of EMF. Okay. Any question? Boleh try verify. Based on calculation value that we have discussed just now, then you can substitute the value, for example, the value of BDC, rheostat resistance, the duty ratio, then you verify. Is it the motor can obtain the desired speed, 1,200 RPM? Right. This is created and share the result instantaneously from the information. Change the cost means the stage. Yes, so now I just don't know. It makes sense. AI. So you add component current measurement, current measurement. Maybe you can measure the average of the baby. So the meaning of it.